Okay, so the last couple of videos we focused on calorimetry and heat changes in that way, and that's a way to figure out the enthalpy change or the energy change in a reaction or what's going on. But we're going to do a different way today, and we're going to talk about Hess's law. So if you open up with me in your notes, it's page 21, and we're going to be dealing with Hess's law. Now, enthalpy, we've said before, is a state function. What does a state function mean? It means it does not matter how you get there, it only matters that you got there. So one of the examples of a state function is when a reaction takes place in a series of steps, the overall change in enthalpy is the same as if it took place in one step. And let me give you an example in this particular case here. So they're showing you a graph here where they're saying that there's two reactions that occur here. We have N2 plus 2O2, and that's taking us to O2 plus 2NO. And then there's a second reaction that is O2 plus 2NO, and that's taking us to 2NO2. So if you take a look here, in order to get for reaction 1, and this is reaction 2, reaction 1 right here, we have to put in a significant amount of energy to get from here to O2NO. But then reaction number 2, to get from 2NO plus O2 to get back down to NO, we actually lose energy. So the end result of that reaction is those two different changes in enthalpy being added together, and the end result is we have to put in 68 kilojoules altogether. Now, that would be the same as if we just wrote the reaction like this and said, oh yeah, we're going to go like this, and we're going to put N2 plus 2O2, and it's going to go to 2NO2. Do you see how, if you take a look at the above equation, what we simply did is we canceled out what we call intermediates. See how this unit here cancels out with this right here? And this right here cancels out with this right here. And then this and this stay in the equation, and this stays in the equation. And so what we can always do is we can always add up the individual enthalpies of reaction steps and end up with the overall enthalpy in an equation. Again, I'm telling this to you, and you may be going like, what the heck are you talking about? Well, there's some steps here. And I want you to have these kind of at your disposal, because what ends up happening often is that whenever we have a series of reactions, in order to get from our reactants to our final products, we have to rearrange our reactions back and forth until we get to our final product, which again sounds really, really kind of weird. So probably the best way to do this is by doing the example. But before we do that, if you ever happen to take an equation and you flip around the equation, the change in H for that equation ends up being flipped. Second, if you ever have an equation and you multiply that equation by a certain coefficient, whatever the change in H is for that also comes up that. So if you multiply something by 2, so if I multiplied this equation right here, that has a change in H of minus 393.5 by 2, then that would be double the enthalpy change. Yeah. If I flipped it around, instead of being negative 393.5, it would be positive 393.5. And what's interesting here is that change in H is given in joules per moles, which means if you change the number of moles, you have to adjust the change in H. And we'll talk about that when we get to it. But probably the best way to do this is to try and solve a problem. And typically what will happen is this. They'll give you an overall equation. So in this case here, here's our overall equation. And they're saying, hey, here are two equations that we used to get to this. Now, all we're really trying to do is kind of like a puzzle. We're trying to flip and match the individual steps to try and get to this equation. So if we take a look at this from the start here, what we're going to do is we're going to try and find things that are only appear in one of these equations and only appear on one side. So if you take a look right here, let's start with this first C. There's no place other than the first equation where we have a C. And if you notice here, we have one C here and we have one C here. So the chances are we're just going to leave this equation as it is because we need to have our C in that spot. Then we go to our second equation. Now, if you take a look at this here, and this is kind of a big deal, when we look at this, we need to end up with the CO, which is on this side. Don't we then need to end up with it on this side? Now, I may look at it and go, oh, wait, but we have a plus 1/2 here. We have a plus 1/2 here. Yeah, but don't we already have an O2 on this side? So if we need a plus 1/2, would you agree with me that if we put and it's kind of like any sort of math equation. If you have something on one side of the equation and something on the other side of the equation and they're the same, they cancel each other out. So if I were to take this equation right here and I were to reverse it, wouldn't I end up with this? I would end up with CO2 on this side going to CO plus 1/2 O2. Now, as soon as I flip that, that means that I'm going to change the sign of this as well. So now my change in H for this equation is going to be plus 283.0 kilojoules. Now, once I've done that, this version here does not exist. So if I've done this correctly, it's kind of like an arithmetic problem. If I add these two problems together, this right here and this, I should end up with this. And if that's the case, then I can, again, this gets canceled as well. I should be able to add this and this together and end up with our overall change in H. So let's see if this works out for us, yeah? So if you take a look here, don't we have a C right here to start with? And we have an O2 on this side. But don't we have a O2 on plus 1/2 O2 on the other side? So if we get rid of this, wouldn't that leave us with plus 1/2 on this side? So we're going to go plus 1/2 O2 here. By the way, I'm kind of flying loose with the solid and liquid and gas states, and that matters because a solid cannot cancel out a liquid form of the same thing, because a solid and liquid, when you deal with their changes in enthalpy, they're different. So we have plus 1/2 of that. So we've taken care of the top equations side. And then don't we still have CO2 over here on this one? Yeah. But if we write CO2 right here, right, let's just jot it down. Isn't there a CO2 on this side over here? I'm just going to write it down, all the things that we have, plus CO, right? If I do that, won't the CO2 here and the CO2 here cancel? And our end result, won't it be C plus 1/2 O2 goes to CO, which is exactly this right here. And all we did is we just flipped the second equation around to make that happen. So anytime you have a series of steps, you can kind of add them as if they're an arithmetic problem and cancel out units that are on opposite sides to end up with an overall equation. And if you have a series of steps, all of the intermediate steps, they'll cancel out to end up with your overall equation, which I did here, but I kind of drew it kind of wonky. This right here is my overall equation. Now, what's really important is we want to know what the change in H is. And so in this case right here, we'd have to add these two values together. We have negative 393.5 kilojoules from the first reaction. And then in the second reaction, we have to flip it. We have to add 283.0 kilojoules. And we add both of those together, we end up with a change in enthalpy for the reaction. And I'm just putting the Rx in there just so we know it's for the overall reaction of minus 110.5 kilojoules. That's an equal sign right there. So this is an exothermic reaction, pretty likely to occur. Let's try another one. Now this one is going to be a little more tricky, and it's going to require us to manipulate things a little bit. And I'm hoping that you embrace these as kind of fun little puzzles, although that may be too much to ask. I will say this. I'm going to do this right now because I already did this prior to this video to figure out how it works. So it wasn't me instantly going, oh, we should do this or oh, we should that. It takes a little bit of finagling back and forth. So all I know is that I need to take these three equations right here and I need to end up with this equation right here. And the only tools I have are I can flip these around, any of these equations around, or I can multiply them by or divide them by any variable to get to this particular thing. And when I get done, I'm going to add up all of the changes in enthalpy to see what's happened. Now, I looked at this and I went, all right, I need to have N2O on this side over here. And I looked at all of the equations, and the only place I saw N2O was right here. But then I looked at it and went, wait, I need only one N2O, and here I have two N2Os. And so I'm like, all right, what should I do then? I'm going to divide this by 2. So what I did is I took this, and I'm going to write these down below here so it doesn't get confusing. I'm going to rewrite the equations. So I took this entire equation, and I just divided it by 2. So I'm going to write, this is going to be equation 1, 2, and 3. And so I took equation 3, and I divided it by 2. I just want to let you know what I did. And I got N2O goes to N2 plus 1/2 O2. And again, I've gotten kind of lazy with the states of matter. You shouldn't be. So this is my equation. And when I did that, when I divided it by 2, that meant that I have to divide my 163.2, I have to divide that by 2 as well. So, okay, I got my N2O where I want it to be and kind of correct. But then what do I do next? Well, I looked at NO. Where's there NO? And there's NO in a couple of places here. There's 2 NOs over here, and there's 2 NOs over here, right? They're both gases, right? How am I going to set this up in such a way that I end up with 3 NOs? Because, yes, if I have 2 NOs over here, that's already in a good spot. If I flip this around, wouldn't I end up with 4 NOs over here? So I ended up having to do a double whammy here. What I did is I reversed this and I divided it by 2. 2 things that I had to do to try and end up with this as a 3 NO when I added this together with this. Again, if you're looking at this right now and going, oh, come on, man. It does take a little bit of work to try and finagle this. And this problem didn't take me like a minute. I didn't automatically do this. I went back and forth and messed around. I tried to mess around with the top equation first, and by dividing it by half, and then that messed around with some other stuff. So I ended up with reversing this and dividing it by 2. So this is equation number 2, and that is reverse and divided by 2 from the original one. So when I reverse and I divide it by 2, what I end up with is I ended up with NO2 on this side, which still stays as a gas, that doesn't change. And it goes to NO plus 1/2 O2. Again, I reverse the sign of this, which means it no longer is a negative, it's going to become a plus 113.1, and I divided it by 2, so I'm going to have to divide this by 2 as well. And then lastly, I ended up leaving this one completely alone. So this one stays the same, so it becomes N2 plus O2, and again, I'm going to try and keep the states of matter in here, goes to 2NO. And because we did not do anything to it, the change in enthalpy stays the same as plus 180.7 kilojoules. Again, in each of these cases, this is the change in enthalpy. I typically like to write RXN at the end of each one of these because it's the change in enthalpy for a reaction. Now, we're not done here because we have to make sure that if we add all 3 of these together, that we're going to end up with this. So how does that work exactly? Well, let's take a gander at this. So first of all, we can't have any N2s here because there's none up here. So if we look at the N2 that's right here, is there any other N2? Yeah, there's one right here. So I can take this N2 and cancel it with this N2. What other variables do we have in more than one spot? Well, do you see we have one O2 over here? And don't we have a half an O2 and a half an O2 over here, which by my recollection is one full O2. So on this side, I have one O2, and here I have one O2 combined. Are we done yet? Well, kind of, because on this side we have N2O, and this side we have NO2, which are the 2 things we want. And this side, don't we have NO and 2NO? So if we actually do the problem, add them all up, what's left over here, we end up with this. And it forms 3NO. Now, again, let's not forget the states of matter. Now, that being said, we then need to add these 3 values here because the whole point is we wanted to figure out what the change in enthalpy was for the reaction. So when we add up all of these right here, we end up with the change in enthalpy for the reaction as 155.65 kilojoules. And if we were in a world where we did not care about significant figures in any way, we would leave it like that and take off points on the AP exam. But since we have 1, 2, 3, 4 in all of these things, we're going to have only 4 significant figures. So wouldn't that round us to 155.7 kilojoules? So this would be our final answer. Now, the only way to get good at these, and incidentally, over the years, my students have kind of enjoyed these. At first, you're like, come on, man. We're going to do some practice on this. And after you do a few of these, you kind of long for the idea that they might throw in one of these problems. I'm guessing that on a 45-minute exam, they might not. In future years, if you're wondering, that's because this year we only had 45 minutes for our exams. But anyway, I'm going to have you guys do a couple of problems on this next time we meet to make sure that you feel comfortable with this. As always, hopefully this has been helpful. I'll see you in the next video. Thanks. Bye.